All right, this little one is in heat tonight. Okay, so she's going to make a lot of noise and be very vocal about doing our statistics. She's got a lot to say about that, mostly in terms of finding a boyfriend, but she's not allowed to have that. She's got some heart issues, which is why she's not getting anesthetic for that operation. So say hello, serendipity, and since she doesn't like to be called, we're going to go. Okay, so when you hear her, realize she's adorable, worth putting up with. Okay. Yeah, I know I touched you. Yeah, go. All right. Like I said, we might have to break a little bit to take care of that. Like now. Okay. But for the moment, let's get started, and then I'll see if I can't put her into a different room. Okay. All right, so we're going to talk about test of hypotheses today. We're going to do a couple of problems. That way I can make sure that we're not going to be too late here. But what I did here, okay, was let me go here. So what I did here is find some more problems. I just went up, I clicked your ebook, turned to the table of contents. Okay, there's the problems that were in our homework. Okay, but since I think we have a video for those, we're going to do this. Okay, so you can see there's just a ton of problems here left to work with. Okay, I'm going to concentrate more on the word problems because those are the ones I'll tend to pick. Okay, and we'll just go from there. Okay, so we have yeah, we'll do one of these. Okay, general social survey. Okay, GSS asked a sample of 1,228 people. Okay, how much time they spend watching TV each day. You could tell this book was written a while ago because I don't think people watch as much TV anymore. Okay, YouTube notwithstanding, TikTok certainly notwithstanding, Instagram notwithstanding. Okay, we have the mean number of hours was 3.09 with a standard deviation of 2.85. Watch how this problem is written, right? The mean of what? The mean of this sample. Okay, so it's as much a reading comprehension and grammar quiz than it is a math quiz. Okay, perhaps more so. Sociologist claims that people watch a mean of 3 hours of TV per day. Okay. Do the data provide sufficient evidence to support the claim, etc. Alpha equals 0.01. Okay, so let's just get started with writing down the things that we know. Okay, see if I can move me out of the way and move this to something that is useful. I don't want to do that. Really? I'm going to move this over. I don't know how you guys deal with a small screen like this. Okay, I really don't. But there we go. All right. So what we're going to do, okay, watching the TV, we have a sample size, right? We have n equals 1,298, okay? The mean x bar, okay, is equal to, the mean is 3.09. Standard deviation, this is S because it's a sample standard deviation. Okay, that's the big question you're asking yourself when you're dealing with a test of hypothesis. Do I know S? Do I know sigma? Which one do I know? If you don't know this one, okay, then we have to use S, which means we're looking at a T distribution. But if we know the sigma, then we're going to be able to get a Z distribution, okay, a Z interval or a Z test rather than a T test. Okay, that's really your biggest issue when you're dealing with this. Okay, he did the study, she did the study, whoever. Okay, and they came up with the mean number of hours. Sorry, this is mu. Okay. Okay. All right. No, this is right. This is X bar. What am I doing? Okay. So sociologist claims that people watch a mean hour of TV. So this person said, I think it's 3.00. It says, do the data provide sufficient evidence to disprove the claim? Okay. So how do I know what to test the hypothesis? Although I opened up to chapter 9, you see this level of significance terminology? The only place this comes up is in chapters with test of hypothesis in it. So if you see this level of significance business, you know, excuse me, that we're doing a test of hypothesis. Okay, it's the only place where this shows up. So you also have little cues like test the claim. Okay, but that's the big one for me is like, hey, the level of significance is. So we're going to claim the researcher is right. 9 hours of TV. We've got time for that. It's not enough good TV like that. Okay. So we have mu is equal to 9. 3. Okay. Okay. And H1, right? I'd like to say, you know what? I don't think they watch 3 hours of TV. Okay. Now, usually, I picked a kind of a bad first example. You could make the argument that they watch more, and I would be okay with that. But as it is, I would a careful reading of this thing. I'd say they watch about 3 hours of TV, and is there sufficient evidence to disprove the claim? So I'm not going to make a claim about whether or not people watch more or less. I'm just going to say it's not 3. Okay, that's all. That's my reasoning for this. And I think the question I picked for the test is a little bit clearer, clear direction on which way you want to go. Okay, we're going to say alpha is equal to 0.01. Okay, so now we're going to set up our test statistic. Okay, we're going to say our mu is going to be 3. We're going to do a not equals to. We have an n of 1,298. We have x bar was equal to 3.09 and s was equal to 2.87. Okay. How do you know it's a normal distribution? Look at your sample size. Right, that is way bigger than 30, so it's going to be okay to have x bar be normally distributed. All right. So that's how we're going to know. Okay. So that's what we want to type in. Okay. Next thing we're going to do is we're going to look for a t-test in our calculators. Okay. So here we go into the calculator. All right. We're going to go to statistics. So actually, we don't need second function. Stats, tests. Okay. T-test. Okay. All right. We're going to just type stats. Okay, and notice that most of that other stuff got pushed away. We do not have 1,298 pieces of data to put into our computers. We're not doing that. Okay, so here's our 3. Okay, x bar, we got a 3.09. Okay. Let's see here. All right, well, very noisy today. S 2. What was that? 9787. Okay, hold on a second. All right. And that was the big one, right? That was 1,298. Okay. We want to know it equals 2. And again, if you made a different argument with that, I could easily understand, like, well, you did the study, it was more than, you want to say it's 3 instead of something else. I could buy that argument. Okay. So here we go. Here's our results. We have our t is equal to, okay, our t stat is equal to 1.12, 1.1, called 1.13. Our p-value is 0.2588, rounding. Okay. And then we can go ahead and do that. So how does our p-value 0.2588 compare to 0.01, right? So it's like 1 cent, and that's like a quarter. This is definitely bigger. So our p-value is larger than 0.01. Okay. And I apologize. I know I told this story before, but this is the story. This is how I remember it. Okay. When I was growing up, there was this housing development called Love Canal. No, I'm not kidding. Okay, it's the 70s, 60s actually. The people that built the housing development, they built it on top of like land that had been abandoned by power companies because they were too toxic to have people working there anymore. Okay, they didn't care what they were doing. They would just dump solvents and other stuff, outside. It just they didn't really keep track of everything. Okay, they just dumped a whole bunch of crap on the land. And then the housing development people came by and said, "This is a good place to make some houses. Let's do that." And they sold them to people. This is like upstate New York. And then all these kids, the kids that were born there started getting like all these weird and rare birth defects and weird and rare childhood cancers, just a lot of them. And the power company was like, "Look, it's that's sad and unfortunate. We're very sorry, but this is not our fault. You can't say that. Just because you built a house on top of a toxic dump doesn't mean that we're at fault." So they had to go through, and you have to do a statistic. You have to say, "Look, it's unlikely that other people are going to be at fault. This is rare." Chemical companies, power companies will say something like, "Look, so okay, so what that well, not so what, but it's tragic that 15 out of 20 kids in your first grade class have leukemia, but that's random chance." And you go through and you show that it is so improbable to have 15 kids out of 20, right, have leukemia, that this can't be by random chance. Okay, it wasn't just like, wow, you just got the unluckiest draw ever, right? If you play Dungeons and Dragons, you roll your character up, you're like a 3, okay, a 3 again, 3 again, 3 again, and all 6 stats are 3s. And then when you go to roll your hit points, you get 1. Okay, like that person is just not fit to go outside. All right, they're not going to make it in that world. But the likelihood of you getting all 6 threes is, no matter how you want to do it, it's nearly impossible. It is a possibility, right? You can calculate that, but it's unlikely that it would ever happen. Okay, so the same kind of thing here. It's like you don't get to make that kind of probability and say, just unlucky, I guess. No. So if your probability here is really, really small compared to your standard, then no, it isn't by random chance. There's a fault here. So in this case, the probability that you could have gotten this result is about 25%. Okay, 26%. Your standard was 1%. You did not fall underneath this standard. Okay, so in this case, you're going to have to say, do not reject HL. Okay, this is not a tiny probability in comparison to 1%. It's a rather large probability. 2% would be a large probability compared to 0.01. Okay, anything that's bigger than this, you say, well, this is the limit, right? And one out of 100 kids are going to have peanut allergies, and no, that's a bad example. There's a 1% chance that something's going to happen. You get 25. It's not an unusual event. Okay, so we're not going to reject the null hypothesis. We're going to say it is likely that people watch 3 hours of TV per day. Okay, so that's the kind of thinking you have to have with this. All right, but that's what we're looking for. So on your exam, on your quizzes, if you just write this, you're getting it wrong. Okay. You have to explain in the context of the problem what your answer means. Okay. Do not reject HO. Great. What up? What are we doing with that? Because you think you're going to have to explain this to somebody who has not had statistics, or perhaps not had it in several decades. Okay, they're not going to remember. You reading an article, right? If you're a nursing student or you're, something like that, if you have to read research articles for your profession, they're going to say we didn't reject the null hypothesis at the 0.001 level or something. So if you write a scientific article and you write we didn't reject the null hypothesis at the 0.01 level or something, you can write like that. But if you're reading it, you have to be able to interpret we didn't reject the null hypothesis. What does that mean? Okay, so it's a thing you kind of have to interpret and turn into regular words. Okay, I know the book has a lot of formality to it. That's fine, but you have to explain this to your boss. They want an answer. They don't want, well, it's this, that, or the other. Okay, so be careful with that. All right, now this book is notorious for doing something like number 23. We will not be doing this. I do not ask you questions like number 23, because it says for the following outstanding credit card balances for a sample of 16 college students, we end up with these numbers. Okay. Following is a dot plot of the data. Is it reasonable to assume that conditions for performing a hypothesis test are satisfied? Now, the two conditions you're going to need is population is drawn from normal distribution. Okay, that doesn't mean use normal distribution properties. It just means like we're free and clear to use a null hypothesis with a t-step to the t-test. Okay, and two, okay, this is the more important one. No outliers. Okay, may not have outliers. Okay, now what if it's not normal? If like you have a dot plot or a histogram that would look something like this. All right, so you might get a distribution like this. Okay, like a histogram. Certainly is not normal. There's no outliers. Okay, but it is not normal. So you should not use it here either. Or if you have a dot plot, histogram looks something like this, but you've got points out here, like that's an outlier. You shouldn't use it. Okay, this one, that's like playing which one of these is not like the other. Okay, this is not. Oops, go back. Oh, jeez, it's going to do all of that for me. Book contents, chapter 9, sections 9.3. And then we're just going to go all the way down. Okay, so the book actually does give you problems like this, but I don't think they chose any from the homework. And your answer to this, okay, when they come by and they say, hey, does this work? According to the reports, if appropriate, it's not appropriate, you're done. Okay, you don't get problems like that with me. I'm going to give you, if I gave you a problem, you can solve it with the technique that you have, or one of the techniques you have at hand. Okay, I don't do that to you. All right, this one, I feel a little bit weird about it, right? Because it's kind of got a long tail to it. But nothing is coming off flagged as an outlier. So even though it may not look entirely normal, this is it's vaguely mound shaped. So we're going to call it yes. Okay. So everyone I give you the answer, like, should you do this? Yes. Okay. So we have some points here. So we have what? A psychologist is designing an experiment with rats will navigate a maze. 10 rats run the maze. And the time it takes, excuse me, let's see about her again. Oh, jeez. There we go. Okay, so we have some numbers here. Okay, here's the time it takes for them to complete the maze. I guess they are doing this in seconds. Okay, and let's see. Psychologist hopes that the mean time for the rat to run the maze will be greater than 60 seconds. Okay, so that's what we're going to do. Okay, notice they didn't give us a mean or standard. Well, they gave us a mean, kind of. They gave us 60 seconds. Give us a benchmark. Okay, so all right. It is possible for doing this. Actually, I'll bet it isn't, because look at the ones that do give you what it's possible. Is they tell us, they say alpha equals. Okay. So in this case, I would suspect they would say, no, it's not normal. We shouldn't do it. We're going to do it anyways. We don't. Okay. I hold up a bunch of, yeah, they didn't give us an alpha. So I suspect that is not going to be a, by their estimate, that's not going to be a good one. Okay. But yeah, let's use a whole bunch of problems for problems you're not supposed to do. So we're going to say this point is 60 seconds. Okay. Greater than 60 seconds. Okay, alpha equals. They didn't give us one. If you are ever in charge of coming up with a test and you don't have like other people that have done this before, and they say like maybe you're in a criminal justice class and like, well, you took statistics and you figure it out. Alpha is 0.05. Okay, like in most academic settings for most things, alpha is equal to 0.05. Okay, if you're nursing, you might change that. Okay, because every field kind of has its own standard. But for academia in general, 0.05. You ever have to go serve on a jury? Say what's reasonable doubt? Say anything more than 5%, or sorry, anything 5% or less is reasonable. So 5% is reasonable doubt. Okay. More than that would also be reasonable doubt. So yeah, 5% or more would be I doubt you. Okay. Sorry, said that backwards. Okay. So our test statistics. Okay, this is where we're just going to write down everything. Okay, so we're going to say that, well, we have some data. We're going to type that into the calculator. All right. We are going to, we don't know the standard deviation because we're typing it in. So that's all on you. So it has to be a t statistic because they don't tell us any other number here. And since you figured it out, you don't know what sigma is. Okay. We want mu 60, and we want n to be, and you're not going to have to tell them this, but 2, 4, 6, 8, 10 rats. Let's go to the calculator. So we're going to go hit stat. Okay, we're going to clear my list 1. Remember how to do that. So, okay, now we're going to go to list 1, stat, edit, list 1. We're just going to take these things in, right? So, okay, 6.3, 55.6, 68.1, 42.1 with a little speedster there, 52.5, 60.9, 8.3, because I got distracted, 69.2. Imagine it's pretty easy for a rat to get distracted. All sorts of interesting smells in there. Okay, so let's go to stat. We're going to go to tests. We're going to go to t-tests. Right, oops, stat, t-test. Why can I not press buttons today? Okay, we're going to go to data instead. Okay, so notice it asks us like, where's your list? It's in 1. Frequency is going to be 1. Okay, they want to do 60 seconds, and they want greater than, right? Well, greater than 60. Okay, calculate. Okay, and there's our value. So we have a t-statistic, right? A test statistic, and that is equal to 0.52. Our p-value is 0.3063. 3063. Okay, and again, we're getting one that is way bigger, right? So I'm sorry that both of our examples turned out to be the same deal. 0.3063 is larger than 0.05. So do not reject HO. So even though, look here, the mean turned out to be 61.45. So the mean was 1.5 seconds more than what the expected was. It's not large enough to be a difference. Okay, it's not statistically noticeable. It's not statistically significant. That's what significant means when they came up with this verbiage. It means noticeable. Okay, so if this was like the princess and the pea, no, she didn't notice the pea. She must not be a princess. Okay, so do not reject HO. Rats go through maze. Oh boy. There we go. At 60 seconds. Okay, it takes them 60 seconds to navigate the maze. Okay, so that's what we have. All right. Let me go ahead and get my secret treasure trove of other problems. Okay, that's why I got the book out, because we can go ahead and hit chapter 9, hypothesis testing, but we don't have a homework section for this. We just have determining which method to use. Oh, okay, so it gives you kind of a little flow chart in here, right? And bigger than 30 and is less than 30, and kind of go through this. Okay. I wouldn't memorize that because it's not that. There's stuff in here that we did not cover in the chapter. Okay, like number 18, they want to know what's going on that the standard deviation is different. We did not use that problem. Okay. Okay, so number 16, this is not a t-distribution. Okay, this is something else. So let's have a look. So this general social survey asked 514 people whether they said they ever considered a career in science. 178 people said that they had. Okay, so you probably do not, if you're my age, you'll remember TV commercials. Sorry, it's tea. It's not beer. Okay. There used to be commercials like 3 out of 4 dentists recommend you use toothpaste, and that's a proportion. Okay, so you could rewrite this as 178 out of 514 people said they want the career. Okay, so that way, like, notice what else they gave us. Did they give us a mean? No. They give us a standard deviation? No. They didn't say anything else. They just said 300 or 178 people out of 515 were interested in pursuing a career in science. Okay, great. So this one, okay, use that alpha equals 0.05 level of significance. We know it's a hypothesis thing. But what are we going to do? We're going to look at the 0.3. So we're going to say P hat is equal to 0.3. Change the decimal or change the percent to a decimal. Okay, biggest mistake, well, not the biggest mistake, but one of the common mistakes people made was not changing this percentage to a decimal. You have to do that. We have alpha equals 0.05. Now we're going to have our test statistic. How many people said yes? So do you want a career in science? How many people said yes? That's your X. 178. How many people did they ask? 514. Okay, so look here to the problem here. All right. So we're going to go to stat. We're going to go to tests. Okay. Now what we're looking for is we have one interval, one proportion. We're going to do a one proportion z test. Okay. Right there. One proportion z test. So our probability is 0, or p sub 0. I used hat, I apologize. 0.3 out. Our x, well, we have 178 out of 514 people. Okay. And again, they wanted greater than, so this is fine. Okay. Just going to calculate and have at it. Okay. So our test statistic, proportions are always z. Okay. So our z stat is equal to 2.29. Okay. Our p, we're looking for not p hat, that's what we calculated. Okay. It's p, just p. Okay. For p value. Okay. And this is 0.010. 0.110. Okay, so this is 1.1 cents. Okay, so which is bigger? This is my p-value. This is my alpha, 0.05. Which one's bigger? Would you rather have a nickel or a penny? Rather have a nickel. Okay, so my p-value is now smaller than, this was my standard, was 0.05. You didn't make that standard. Okay, so we have to say, well, there's got to be an alternative explanation for what's going on here. Okay, so we're going to say, reject the null hypothesis. Right, p-value is smaller. Reject the null hypothesis. We can conclude that there is evidence to say that more than 30% of people wanted a career in science. So we're going to say yes. More than 30% people expressed interest in career in science. Okay. Again, the more formal way to say it is there is evidence to suggest that more than 30% of the people wanted a career in science. Okay, but there we go. Okay. Let's see here. There's another population standard deviation. We're not doing that because that wasn't part of the problem. That wasn't part of the chapters. Okay. Like the one that wasn't exactly worded the same way. Okay, let's actually go to test. I always remember when I took, I think it was Calc 1. No, it was Calc 3. I'm trying to remember which teacher I had. And I got something wrong on an exam. I blew it. I really blew it. I was like, hey, did we get one of these? She went to the chapter review, pointed at it, said, there, right there. Oh, I have no case. Thank you very much. Okay. So it was a problem, just like one that, if I had paid attention to that, it was just a slightly different wording, and I was like a little bit used to it. But she pointed that out, and I was like, never mind, thanks. After that, I did all the problems in the chapter reviews, or at least all the ones I could do, because we don't always hit everything in the chapter. So you have to realize, like, oh, they're asking about standard deviation. We're not doing that one. Okay, let's look at tattoos. Okay, Harris poll taken in 2016. Okay, 423 people had 423 people had one or more tattoos. Can you conclude that the percentage of adults who have a tattoo is less than 25%? All right. Oh, Harris poll taken surveyed 2016 adults, not the year 2016, the people. The survey is 2016. Okay. So we have HO, H1, right? Alpha equals, right? You know, it's a test of hypothesis. So we're going to say, again, this is 423 out of, so we're going to go over here a minute, 423 out of, okay, 2016 people have tattoos, or one or more, okay? So that's how you know it's a proportion. They didn't say, like, what, you know, it's a yes or no question. So that's another way to tell. It's like a yes, do you have a tattoo? Yes or no? Not how many square inches does it cover, not how much did it cost you to get it, not how long did it take to put it on, nothing. Just, do you have a tattoo? Yes or no? Okay. So we're going to say P is equal to 0.25, or we think maybe less than 0.25. Okay. So there we go. Okay, my alpha, what was my alpha? Alpha equals 0.01. Okay. Now for our test statistics, right? This was step 1, step 2, step 3 here. Test statistics. 423 out of 2016 people. Okay. We don't really need anything else. Okay, we're about done. Okay, notice they use a percentage. Okay, we got to convert that to a decimal. Do they say anything about a mean? No. They say anything about a standard deviation? No. It's proportions. Okay. So be good at spotting what kind of problem it will be. Your life will be a lot easier if that's the case. Okay. So here we go. We have stat. We're going to go 2 tests, 1 proportion z-test. Okay, that's the one we want. If you wanted 2 proportions, we didn't do that in the book. We're not going to. You want to say like the success rate for Alcoholics Anonymous versus the success rate for more traditional therapy, quitting alcohol, and you would want to you would want to compare those 2 proportions. Okay, that's what a 2 proportion z-test would do. This is just one. We're just comparing it against the standard. Enter. Okay, what are we comparing against? We're comparing against 0.25. Okay, that's the value that we want here. And we said X is 423 people out of 2016. Okay, and they think, excuse me, it is less than 25%. So we're going to go ahead and click this one. Okay, they want less. Okay, calculate, enter, and go with that. So our z value, okay, is negative 4.17. Our p value is what I'm glad I picked this one. Do you see this -5 here? That means there's 5 zeros. The decimal place means 5 times. So it's 1, 2, 3, 4. There's 4 zeros and I don't want here. Okay, so this is 1, 2, 3, 1. Here, 0, 1, whatever. Okay, 5, 4, etc. That's what that means. Okay, so we have to compare this number, 1.54 times 10 to the -5, okay, versus 0.01. Which one is bigger? Okay, this is a much smaller number than this one. Okay, so we're going to say, reject. I'll spell tonight. Reject HL. Okay, It is likely that 0.25% of population, or less than 0.25% of population has a tattoo. Okay, so that's what we have there, or at least they will. Those are the people that will admit to having a tattoo, I suppose. Okay, I don't think that's the stigma for it is not that big deal anymore. So I can't imagine why people would say yes or no, or would want to disguise the fact that they had it or didn't have it. I mean, my accounting teacher recently took accounting a couple semesters ago. She had tattoos. You know, if accountants are going to have tattoos, I can't imagine it's that outside of the norm. Okay, so whatever. All right, it's likely that fewer than 25% of people have tattoos. Okay, so that is how you do those kinds of questions. Okay, and there we go. So I hope that's enough to do those. And you know, you got a little bit of got to meet my guest lecturer at the beginning. So good luck with that. If you need more of those, okay, I can certainly do more. Okay, but watch this one first and let me know. All right, thank you very much, and good luck on the final.